Who's breathing heavy? It's me. So, hey everybody, I'm ShawnSamborsky. I'm a master's student here in the Department of Renewable Resources, much like many of you. And this is my presentation entitled Examining Nitrogen Retention in Soil Amended with Biochar. And I'm going to discuss the effect that biochar exerts on soil nutrient cycling, nitrogen in particular. So let's start with biochar. What is it? It's charcoal produced from biomass, such as wood waste. And we call it biochar when we use it as a soil amendment. It's considered to have substantial agronomic benefits and influences soil physical, chemical, and biological properties. And it also has the added benefit of sequestering carbon in soil for thousands of years. So why are we interested in it? Because we might be able to use it in well site reclamation. Some oil and gas sites developed before 1978 can be difficult to reclaim, as topsoil conservation wasn't a requirement. These sites often have little soil organic material, and establishing vegetation on them is difficult. To combat this decompaction, the use of organic amendments such as compost and chemical fertilizers are often used to reestablish native plant species. And biochar is being assessed as a amendment because of its positive benefits in soil. Two prominent ones are cation exchange capacity and enhancing microbial habitat. To simplify these two benefits, CEC is the ability of soil to hang on to positive ions such as potassium, calcium, and ammonium. Generally, high CEC is a good thing in soil, and it means that your soil has a larger capacity to hold nitrogen as ammonium. Basically, you want your soil to hold on to your nitrogen so your plants can use it later. The second benefit is improvement of the microbial environment. Microbes are important for nutrient cycling and, for example, nitrifying ammonium into nitrate so it becomes plant available. You want your microbes to convert ammonium to nitrate because this is the type of nitrogen that your plant is actually able to uptake. But nitrate isn't held by soil like ammonium is, so once it's converted into nitrate, it just sort of floats around in the soil water, and it can be flushed out if water is added to the soil before the plant manages to take it up. You can think of soil being able to store nitrogen in three different forms, so ammonium, nitrate, and organic nitrogen across these three different pools. Physical, which is basically the pore water like we talked about, chemical, which is the CEC of the soil, and microbes, which are basically the nitrogen that's held in the body of the microbial communities. And it not only stores the nitrogen, but it also converts between those three forms. Which means it's a little bit tough to pin down sometimes as to where the nitrogen's coming from. So my experiment's intended to answer how does biochar influence the size of those three pools and the activities. And what I did was perform a soil vessel experiment, adding ammonium nitrate to the top of the vessel and then flushing that vessel 4 times with water and collecting the leachate each time that I flushed it. The purpose was basically nutrient goes in the top, leachate comes out the bottom. You analyze what comes out the bottom to figure out how your soil has changed your nutrient regime. My independent variables were soil sterilization to remove that biological component, using Ottawa sand as an inert substance against which you can measure the CEC of the biochar, and then the biochar application rates itself. So what did I learn? I learned that with increasing biochar application rates, you get decreasing ammonium nitrate or ammonium leaching, and that's what you see on this graph here. So the x-axis is the increasing ammonium nitrate. The amount of ammonium that came out of the system was the y-axis. So that's that CEC component. Working against that is the biological effect, and you can see that in these two graphs, or three graphs. You can see that ammonium is being retained by the live samples, and then in the autoclave samples you do end up with more ammonium coming out of the system, but you also see more nitrate coming out of the system. So that's that opposing force. So that's ammonium being transformed into nitrate, and then the nitrate being leached out of the soil. So two opposing forces, how do you decide which one's winning? Which one is biochar keeping more nitrogen in the soil, or is it flushing the nitrogen out? To look at that, you look at total nitrogen. So you can see in the 10 and 0 treatments that it's virtually the same as the autoclaved samples, so there's no real difference. But at 25 tons per hectare, nitrogen, total nitrogen, is actually being retained in the soil. So my takeaway from that is it's likely being retained in the bodies of the microbes themselves rather than the CEC of the soil. So again, the conclusions, biochar has an effect of 25 tons per hectare. I added 12 milligrams of nitrogen into the columns, and of that, 2 milligrams was retained. That's about 16%. That's 16% less fertilizer that you might need to add to your site when you're trying to reclaim it. And I guess the takeaway from all of this is understanding the mechanism behind biochar should help us predict what it does in a more dynamic system. And this will allow us to apply it properly. So that's it. Thanks.
So I